All right, in this video, we're going to talk about the multiplication rule, which is a counting method when you can think of an experiment as being broken out into multiple parts. Okay, so I'm going to talk about this first using an example. So we have a box. Okay, let me go ahead and draw out a box. And the box contains 4 balls. It has a blue ball, a red ball, a green ball, and a yellow ball. All right, and we're going to randomly select from this box. Two balls are going to be randomly selected with replacement. All right, so what does with replacement mean? That means that we're going to select one ball. Say I were to have selected the yellow ball. I'll say, oh, that ball is yellow, and then I'll put it back in. Okay, and then when I go and I do my second selection, I could get the yellow ball again, or I could get the blue, the red, or the green. Okay, so I put the ball back in before I pick my second ball. Right, so find the number of events in the sample space S. All right, so I could start thinking about this. All right, so what could happen here? Here's my sample space S. I can list out all of my events, right? One possible event is that I get the blue ball, and then I get the blue ball again. I could get the blue ball, and then I could get the red ball, right? Blue and red, right? And I can continue listing them out. Now, so that I do not miss anything, a really helpful tool when you're listing out every element in a sample space, when you have multiple parts to an experiment like this, is the tree diagram. Okay, so let's help us out in listing out our sample space using the tree diagram. Let's see how that works. So first, we would start with part 1 of the experiment, where I can get a blue ball, a red ball, a green, or a yellow, right? That's part 1 of the experiment. In part 2 of the experiment, if I got the blue ball first, I could get the blue ball again. I could get the red ball. I could get the green ball, or I could get the yellow ball. Okay, if I got the red ball first, I have the same 4 branches, right? For the second part of the experiment, I could get blue, red, green, or yellow. If I had the green one first, I have the same 4 branches. The second ball could still be blue, red, green, or yellow. And then if I had the yellow ball first, the second ball could be blue, red, green, or yellow. All right, so this is your tree diagram. And the way we would read this is we would say, okay, so we have, let's see, let me use different colors. So I have blue, 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 blue. All right, I can use capital letters here. I have blue, red, blue, red, blue, red, right? Blue, green, blue, green, blue, yellow, blue, yellow. And then I'd go on to red, blue, etc. Right? I can continue listing all of these elements of my sample space until I get to, last one will be yellow, yellow. Okay? But the question doesn't really ask me to list out all of the elements of my sample space. Right? I don't have to do this list. Rather, I just need to know how many are there. Right? And since each piece here on this side represents an event on a sample space, I could just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's going to be 16 total events in this sample space. Right? Is there a quicker way I could have gotten there? Absolutely. Notice that there are 4 different possible events, or 4 different possible elements in part 1 of the experiment. There are also 4 different possible elements in part 2 of the experiment. 4 times 4 equals 16. This is the multiplication rule. Right? So notice we're multiplying the number of possible events in each part. All right, the total possible number of events in our sample space will be that product. So let's change up the problem a little bit. Let's ask, what if 3 balls were selected? 3 balls were selected with replacement, right? If 3 balls were selected, we'd have 3 parts. Part 1, selecting the first part, or first ball. Part 2, selecting the second ball. Part 3, selecting the third ball. First ball can be blue, red, green, or yellow. And then we'd have 4 branches. Blue, red, green, or yellow. And then I'd have 4 more branches for each piece. Blue, red, green, or yellow. Each piece would have 4 branches. I'm not going to write them all out because it would take me a really long time to draw all these different branches. But what I want to note here is I have 4, let me write it here in yellow. There are 4 possible elements of part 1 of the experiment. There are 4 possible elements in part 2 of the experiment. And there are 4 possible elements in part 3 of the experiment, right? So this is 4 to the third, which is 64. Right, so the total possible number of ways we could get 3 balls selected with replacement is 64 total possible different ways. All right, what if I were to change this up a little bit more and ask now, what if we selected 3 balls without replacement? Okay, so without replacement. Okay, so we have part 1, part 2, and part 3 of the experiment. The first ball can be blue, red, green, or yellow. Now, since we do not replace the first ball, we need to be careful here, because when we get the second ball, if the first was blue, then the second ball can only be red, green, or yellow. All right, and if the second ball was red, then the third ball can only be green or yellow. Right, and you can think through all of your different branches here, but we don't actually need to come up with our sample space. We just need to find out how many elements are in this sample space. So I can say, okay, well, how many elements are possible in part 1? There are 4. In part 2, since 1 ball has already been selected and you do not replace it, there are only 3 possible choices. In part 3, since 2 balls have been selected and were not replaced, you have 2 possible choices. Okay, so what do I have here? Total number of events in this sample space is 24. All right, so just to summarize what I've said thus far, what is the multiplication rule? So for an experiment with k parts, okay, the total number of events in the sample space is n1 times n2 times all the way to nk, where n sub I is the number of elements, right? It's the number of possible outcomes in the ith part of the experiment.